Okay, still working in section 7.3 here. We're going to talk about solving linear systems by the addition method. We also sometimes call this elimination. I generally call it elimination because the nature of what we're going to do here eliminates a variable. Okay. And so what we're going to do is the following set of steps. This is similar to the process with substitution. We got a set of steps that if we follow carefully, okay, we should be able to solve any system. So if necessary, rewrite both equations in the form ax plus by equals c. So we're going to write both equations in standard form. Okay. If they're already in standard form, then we can go ahead and skip that step because we already have it done. And then part 2 says, if necessary, multiply either equation or both equations by appropriate non-zero numbers so that the sum of the x coefficients or the sum of the y coefficients is 0. Okay, we're going to see, it seems rather confusing, but we're going to see what that means in just a minute. We're going to add the equations once we do that in step 2, and when we get the sum of those two, we're going to have an equation that has one variable, and then we're off to the races. We can find that one variable, and then we can plug it back into one of the two originals to find the other variable, and then we can of course check just like we did in our other type. So let's see how that works. So if we do this one with the addition method, okay, we have two that are already in standard form, so step 1 is good. Okay, step 2, okay, if we were to, this is what you want to ask yourself in step 2, if we were to add these column by column right now, okay, would the x's drop out or would the y's drop out? Okay, would they cancel each other out? And the answer of course is no. So what we want to do is either multiply one or both equations by a strategic number so that when we do add them, okay, something will drop out. Now for me, I would recognize that there's a plus and a minus here, which is generally a good thing because we want to add and have them be gone. If that were an 8, okay, then we could add those two and the y's would be canceled. Okay, so to make that an 8, then I would need to multiply the whole entire equation by 4. Okay, so if you look on the next slide, okay, they chose to do it the other way, okay, which is to multiply the top one by -3. Let me go back, because again, there's definitely more than one way we can do this. I would have chose to multiply by 4 and get 8 in this column, and then I would have had 12x plus 8y equals 192. And then again, I don't need to change this equation at all. Okay. And when I added those two, I would have gotten 21x. That column would be gone. And then equals over here, if I do 192 minus 24, okay, I'm going to get 168. And then if I divide by 21, then I get 8. So I get x equals 8 here, and then from there I would go and resubstitute this in for one of these two x's, and then solve the equation for y, and then I would do my check. Okay. So let's see if they got the same thing going the other way, where we, instead of getting rid of the y's, okay, we could also get rid of the x's. It's basically our choice, because if we were to multiply this 3 by -3, okay, we would make -9 in that column, and therefore the x's would cancel when we add. So let's see them do that. So they chose to multiply the top one by -3. And again, it's the entire equation by -3, not just the x. So when we do that, they added. Okay, when we divided, we got 12. Okay, because the x's are canceled. So if we divide by -14, we get y equals 12. And then, of course, when they got y, they're going to need to find x. So they took the 12 and they plugged it in. Okay, and they solved that resulting equation, and notice what they got. They got x equals 8. Okay, had we continued our solution, we would have gotten 12 for y. So illustrating that it does not matter which variable you eliminate, it's totally up to you. You can decide whichever one you think is the easiest to eliminate. I personally would have chose the way that I chose because of the fact that there was already a plus and a minus situation. Okay, therefore I didn't have to multiply either of the equations by a negative, and I could go from there and I could find 8 first and then find 12. And of course the check part is plugging those two in and making sure they both give a true sentence. Okay. Now, there's a couple things that generally happen here when we're solving systems. Most of the time when we solve systems, okay, we get exactly one ordered pair solution. The examples that we looked at today have only had one solution. Okay, that means that the two lines that we're dealing with intersect at one point. Okay, all right, and we generally, there's a special name for these types, and this is what we call an independent system. Okay. Now, there is a possibility that we get no solution, okay, and that ultimately means that there's no intersection point, which means the two lines are parallel, okay, and we call that a inconsistent system. Okay. And then finally, there's infinitely many solutions if the two lines are identical. Okay, means that they intersect at every point. Okay, we call that a dependent system. Okay. So you can see the pictures below here. This would be an example if we were to graph and find one solution. That would be an independent system. This would be an inconsistent system, and this would be a dependent system. Okay. So let's take a look at how that might happen. Okay. Ultimately, if we were asked to do this, I would use elimination here. Okay. You could use substitution if you wanted to, but you'd have to solve for one of the variables here, and you'd wind up with fractions, which is going to make your work a little bit more difficult. So I would use elimination here. And they went ahead and did the same thing. They multiplied. Notice that that in either case, if I multiply this by one number, it's not going to give me 6. Okay, so I'm going to have to multiply both to give me a common number here. So they chose to eliminate x's by making these both into 12s. Of course, one's going to have to be positive, one's going to have to be negative. So they chose to multiply the top one by 3, which gave us this equation. The bottom one by negative 2. Negative 2 would give me negative 12 here, which again is going to set up an elimination in x. And if we do that, notice that not only did it set up an elimination in x, but it also eliminated y's, which gave us 0 equals 12. Okay, this is a special case. When we have a system that winds up having no variables in it when we get done, okay, then we have to ask ourselves, is this a true sentence at the end? This 0 equals 12, is that a true sentence or is it a false sentence? Okay, and ultimately if it's a false sentence, okay, that indicates that the system has no solution. Okay, and we say it's the empty set or no solution, and that tells us about these lines that they are parallel. Okay, there is no intersection point between those two. Okay, now if we look at another example, this one we could use substitution for. Okay, if we were to substitute this stuff, okay, in for y, okay, and solve the resulting equation. And let's see what happens this time when we do that. If we were to take that stuff and put it in for y, again in parentheses, and we do the math on that distributing part, we wind up with 15x minus 15x, which means we have no x's. The x's are gone. And notice this time we wound up with a true sentence. And with that true sentence, okay, we know that this is going to be true always. Okay, so this system is always true, and hence we have infinitely many solutions, indicating that these two lines that we were given are the same line. Now, not that easy to tell that they're the same line because they're in two different forms when they were given, okay? But they are in fact the same line. If we were to graph this one and graph this one, we would be graphing exactly the same points. So therefore they would intersect at every point, and hence we say there are infinitely many solutions. Okay, just a couple other ideas involving systems, as we often use systems to model different real-life situations. We're talking about a revenue and a cost function here. A company produces and sells X units of a product. Okay, the revenue is always going to be the price per unit sold times X, which is the number of units we sold. So for example, if we sold 10 glasses of lemonade at 50 cents a piece, if we multiplied those two, we would get the revenue. That's how much money we would bring in. Okay. A cost function here would be if there was a fixed cost, like if we were doing a lemonade stand, we'd actually have to buy the ingredients. That would be our fixed cost. Okay, and then our cost per unit produced, if it costs us 2 cents to make every lemonade glass that we sell, then it's going to be 2 cents times how many we sold. So this is going to be our cost function. And ultimately the point of intersection of the graphs of these two is what we call the break-even point. Okay, if we break even, these are going to be where these two functions intersect. Okay, and ultimately if we're in business, then we want to be on the other side of the break-even point so that we're actually making money. Okay, so let's take a look at an example here. This company is planning to manufacture radically different wheelchairs. The fixed cost is $500,000 and it will cost $400 to produce each wheelchair, and each wheelchair will be sold for $600. So we're going to write a cost function. So we know that from our previous slide that the cost is going to be the fixed cost plus the cost per times X, and the revenue is going to be the amount brought in times X, and then we want to determine the break-even point. Okay. So let's see what they did on the next slide here. We have the fixed cost, as I mentioned, plus 400, which is the cost per chair, times the number of chairs. This is going to be our cost function. And our revenue function, we're bringing in $600 for each chair we sell. So this would represent the revenue function. Now, we said earlier that the cost and the revenue, when those are equal, that would be the break-even point. So if we were to take a look at the two equations we have, we ultimately have a system of two equations. Okay, which we wrote as a system in this one. We can either use substitution or elimination. It's up to us. Okay, they chose to use elimination. They replaced the y in one with the what y equals in the other. Okay, went ahead and solved that, and we got 2,500. Okay, and ultimately, if we put 2,500 back into either equation, okay, we wind up with 1,500,000, and remember that's in dollars. Okay, so interpreting that, then if we were to look at a picture of this situation, okay, we have the revenue function and the cost function. Of course, if we're under 2,500 wheelchairs, the cost is more than the revenue, so therefore we're losing money. After we get to 2,500, our revenue is now above the cost, so that means that we're gaining money, and of course after that, the more wheelchairs we sell, okay, the more money that we're going to make. But the break-even point is 2,500. We have to sell at least 2,500 wheelchairs in order to get to the point where we're breaking even, and once we get past that point, then we're going to actually be making money. Okay. All right, and finally, one other issue that we have here is what we call a profit function. And when we deal with profit in business, the profit is always the revenue minus the cost. So if we wanted to write a profit function for this particular situation, we would do the revenue function minus the cost function, and then of course we'd simplify that, and so our profit equation would be this. And notice if we graph the profit equation, okay, the profit equation is negative until we get to, guess where? 2,500. Okay, 2,500 is where we start having positive profit. Okay, and ultimately anything beyond 2,500 is going to be where we're going to be making money. Anything before 2,500, you notice the profit is below the x-axis, which means that we're going to be losing money. Okay, if we sell only 2,000 wheelchairs, okay, we'd be in the negative, which means our profit would be negative, which means we'd be losing money.